So a buffer solution's whole job is to somehow hold the pH relatively constant, even though little amounts of acids and bases are coming and going. These get used a lot in lab situations where you're dealing with biological systems, because cells are really, really sensitive to pH. So when people need to do research on cells, they've got to create a world where the pH essentially stays relatively constant. And that's what the buffer solution is all about. A buffer solution is a solution of a weak acid and a matching salt. Salt is just another word for ionic compound. So you've got to get to the point that if you see the word salt, you just think, hey, that's an ionic compound. That protects against pH change with addition of small amounts of acid and base. Now, the buffer solution can't do this forever. Had I taken your 40 milliliters of buffer solution and dumped this whole entire bottle of base into the beaker, we could definitely get the pH to change significantly. Buffer solutions can protect against the coming and going of small amounts of acid and base, but that's usually what you're trying to protect against when you have a buffer solution. You made a buffer solution today from vinegar, which is acetic acid, and sodium acetate. Notice that the acetate ion is present in both of those. That's the criteria for having something that will make a buffer solution. You choose a weak acid. You then look at the negative ion present in the weak acid, and you go pick some kind of ionic compound that's got that negative ion in it. Usually you pick either a sodium compound or a potassium compound with that negative ion, because sodium compounds and potassium compounds dissolve really easily, and there's definitely some advantage to have something that will dissolve really easily. When you got all done building your buffer solution, you had lots of the acetic acid, because that was the vinegar, and it's a weak acid. So remember, like 96 or 97% of it stays put together. But then you also dumped in some sodium acetate, which was the source of this acetate ion right here. The sodium acetate that you dumped in made sure that we had lots and lots of that acetate ion. The goal of a buffer solution is to have lots of both of these things, so that this, the hydrogen ion concentration, holds fairly steady. If you can hold your hydrogen ion concentration fairly steady, that means pH doesn't change much. Because we know that pH is a measurement of nothing more than the hydrogen ion concentration. So if we can find a way to keep the hydrogen ion concentration pretty much how it is, we're going to be able to maintain our pH pretty much how it is. So we need to really protect from two events. We need to protect from adding an acid, and we need to protect from adding a base. And it's really Le Chatelier's principle that can help us understand how this is going to work out. If I add an acid, that's the same as adding more hydrogen ions. If I add more hydrogen ions, I'm adding a product. And we know that according to Le Chatelier's principle, if we add something, the system responds to try to get rid of what it is that we just added. So if I dump in some H+, there, that's me dumping in some H+. The system says, oh yikes, too much product. It's going to start taking the H+, packing it up with the acetate ion, and this whole thing is going to do a shift left. Because there's lots and lots of acetate ions, you've got enough acetate ions to grab every hydrogen that shows up, stick together with the acetate ion, and turn it back into this stuff, which, because it's all together and doesn't lose its hydrogen, doesn't have any impact on the pH. So the function of having lots and lots of this acetate ion in there is that the acetate's job is to grab any extra hydrogen ions that show up and turn them into HC2H3O2. So the acetate ion protects against acid. It's just a little shuttle that grabs the extra hydrogen and pulls it over to the other side of the reaction. If we add a base, adding a base is essentially removing hydrogen ions. When you add a base, what really happens is you add OH minus. That OH minus reacts with the hydrogen ions that are there to form water molecules. So it doesn't exactly directly remove the hydrogen ion, but it turns the hydrogen ion into water, and now the hydrogen ion is missing. We know that if we get rid of the hydrogen ion, Le Chatelier's principle says shift right. The system will try to replace the thing that you took away by making more of it. So the whole system goes this way to try to replace the hydrogen that just got removed. And now we found the function of the acetic acid part of this. The acetic acid part of this has the job of needing to break apart to replace the removed hydrogen. So it's like your storehouse of hydrogen. It's got extra hydrogen stored. This hydrogen isn't contributing to the pH because at the moment it's stuck to the acetate ion. But if some hydrogen disappears, this is like a warehouse. It can fall apart and it can break up, or it can make new hydrogen. So we have really two pieces here. We have the acetic acid piece, which is the storehouse for hydrogen to protect when you add a base, and we have acetate ions that can pack up hydrogen and bring it over to the other side that serve as protection against acid. So the function of the acetic acid here is to protect against addition of base. The overall result here is that you have a way to deal with extra hydrogen. You have a way to deal with hydrogen that disappears because it reacted with base. The net overall result is that the hydrogen ion concentration pretty much stays the same. And as a result, pH pretty much stays the same. And we've created a system that takes advantage of Le Chatelier's principle to protect against any kind of a change in pH when extra acid and extra base ends up being added. But like I said, there's a limit to this. There is a point at which this won't work anymore. You can essentially add so much acid that you use up all the negative ions that are there to protect against acid. Or you can add so much base that you use up all the stored hydrogen ions. And that's what's called a buffering capacity. The buffer capacity is essentially the amount of acid or base that can be added before the buffer system fails. And next time we'll talk a little bit about building a buffer solution, making a decision about what you should use to build the buffer solution, and how to know what the pH of a buffer solution is going to be. But for today, all you really need to understand is that a buffer solution consists of an acid and a matching ionic compound, because the weak acid can replace hydrogen if needed, and the negative ion from the ionic compound can grab the extra hydrogen and pack it up. And so a buffer solution works just based on Le Chatelier's principle by making sure you've got lots of weak acid and lots of negative ions. You can protect yourself using an equilibrium system that shifts back and forth to pack up extra hydrogen and to replace any hydrogen that goes missing.